You know, when we picture a scientific breakthrough, there's this incredibly persistent, like almost romantic image we just default to in our heads.
Oh, absolutely. The lone genius.
Right. You picture Isaac Newton sitting under that apple tree in a quiet orchard, or Marie Curie isolated in her lab late at night with, glowing beakers all around her.
Yeah, it's this idea of a single brilliant human brain just holding all the necessary pieces of a puzzle and suddenly click.
Exactly. The connection is made. All the disparate data streams just align perfectly.
Right. And I mean, it's a beautiful narrative, the classic eureka moment, and it makes for great cinema, but it fundamentally ignores the reality of modern science.
Well, because it's impossible now.
Totally.
Right.
For centuries, yes, scientific breakthroughs did rely upon a single human mind, making those creative connections between different observations. But today, that model is just collapsing under its own weight.
Because there's just too much data for one brain to hold.
Exactly. The exponential growth of scientific literature has reached a point where it is physically and cognitively impossible for an individual researcher to comprehend the full scale of their own field, let alone adjacent fields.
Right.
Synthesis, just figuring out what is already known by other people across the globe,
Right.
that can take weeks or even months of manual reading and cross-referencing.
Yeah, the sheer volume of literature makes that lone genius model nearly impossible to sustain.
Yeah,
You simply cannot fit the frontier of human knowledge into one skull anymore.
you really can't.
Which brings us to the mission for today's deep dive. We are unpacking a massive tectonic shift in how science is actually conducted, verified, and published.
And we're using a very specific map for this shift.
Yes, the newly released Google Anti-Gravity 2.0 agentic ecosystem. And I want to be super clear right up front. For anyone listening who thinks, like, oh, so we're talking about a chatbot that writes a fake essay like a glorified autocomplete. No, this isn't just about an AI writing a paper.
Not at all. If you approach this thinking of standard conversational AI, you will completely miss the magnitude of what's happening. We are moving far beyond, passive text completion assistance.
Right. We're talking about an AI ecosystem acting as a highly structured network of digital researchers, programmers, data analysts, and even peer reviewers.
It is a fundamental shift in the architecture of discovery itself.
So, okay, let's unpack this. Because to really grasp what Anti-Gravity 2.0 is doing, we have to look at the mechanics of how it operates under the hood.
And we have to recognize that we are looking at a fundamental architectural departure from traditional software environments. Because, to understand this new ecosystem, we first need to understand what it replaced.
And why the old way was broken.
Exactly, because anti-gravity didn't just appear out of nowhere.
Right, there is a whole origin story here, and it actually starts with coding. Anti-Gravity originally launched back in November of 2025.
Yeah, but it wasn't a standalone application back then.
No, it was actually an experimental fork, meaning a modified version of Visual Studio Code, or VS Code, which is a massively popular text editor that software developers use to write code. And Google had bolted this secondary agent manager interface onto it.
Right. It was a proof of concept, really. That initial implementation demonstrated the potential of agentic assistance, like having an AI actively help you code and research right within your workspace.
But there was a catch.
A huge catch. It was fatally limited by its environment. Because it was tied to a standard integrated development environment, an IDE like VS Code, it inherited the workspace local indexing limitations of those editors.
Okay, let's define that for a second for anyone listening. Workspace local indexing, meaning the AI could only really see and understand the specific folder or project you had open right in front of it on your screen.
Precisely. An IDE is designed to help you edit the files in your immediate project folder. It builds an index of those specific files so you can search them quickly. But if you are trying to build or analyze complex distributed systems or, synthesize research across multiple disparate repositories scattered all across your hard drive or the cloud, you need what's called cross-repository context aggregation.
And the VS Code fork couldn't handle that.
No, it was trapped in its own little sandbox.
I like to think of that initial VS Code fork as, imagine you have a genius-level researcher, right? Absolute prodigy. But you lock them in a single room with just one filing cabinet.
That's a great analogy.
And you say, solve the mysteries of the universe, but you can only look at these specific files in this one drawer. You cannot leave the room to go to the library. They're going to hit a wall very quickly.
That is exactly what happened. The AI was brilliant, but it was blind to the wider context of the researcher's work. So Google recognized this bottleneck. Which brings us to the massive shift announced at their I/O 2026 conference.
The big reveal.
They made a radical decision. They completely detached the agentic layer from the IDE.
They took the genius out of the room.
They took the genius out of the room, unlocked the door, and gave them the run of the entire laboratory.
Wow.
Yeah. Google Anti-Gravity 2.0 was introduced as a completely standalone desktop application. It operates as an independent layer across macOS, Linux, and Windows.
So it's no longer just an extension living inside a code editor.
No, it is a master orchestrator. It allows users to coordinate multiple background agents, both synchronously and asynchronously, across comprehensive projects that span multiple local folders, cloud drives, and databases, complete with custom, scoped security permissions.
Okay, so it's acting like a hyper-competent project manager for your entire computer.
Essentially, yes.
But to manage all of that data, to read across all those folders simultaneously, it needs serious horsepower. The computational core driving this standalone environment is Gemini 3.5 Flash. Now, I looked at the benchmark scores for this model, and they are wild.
They really are.
The raw speed is blistering. On standardized tests, Gemini 3.5 Flash is pumping out 289 output tokens per second.
Which is an astonishing volume of information.
Yeah, let's put that in perspective for the listener. A token is roughly 3/4 of a word. So 289 tokens is about 215 words per second. That is over 12,000 words a minute.
It's hard to even conceptualize.
Right. Claude Opus 4.7, which was a powerhouse just recently, was hitting about 67 tokens a second. GPT 5.5 was at 71. Gemini 3.5 Flash is doing 289. It is crushing the competition in pure speed.
It is a remarkable leap in output generation. But, speed in this context is only part of the equation.
And that's exactly where I have to push back a little. Because speed is great, I love things being fast. But in science, in empirical research, speed without accuracy is just faster mistakes.
A valid point.
If it's spitting out 12,000 words a minute of hallucinations and fake data, that's worse than useless. It's actively harmful. How does it handle the intense complexity of scientific workflows without just getting completely overwhelmed and hallucinating at warp speed?
That is the critical distinction, and it's a very valid concern. What's fascinating here is that Gemini 3.5 Flash's raw speed isn't just for fast typing.
What do you mean?
It's not just about generating text quickly for the human user to read on a screen. In fact, most of what it generates you never see. That speed enables rapid, complex, multi-step workflows and advanced deductive processing behind the scenes.
Oh, I see. So it's thinking fast, not just talking fast.
Exactly. It uses that speed to run internal checks, verify its own logic, and query databases before it ever shows you a final result.
Okay, that makes more sense.
Let's look at the specific benchmarks beyond just token speed, because that's where the accuracy is proven. On Terminal Bench 2.1, which measures single repository command line problem solving, essentially, how well the AI can navigate a computer's terminal to fix a broken system, it scored 76.2%.
Okay, so it actually knows its way around a computer.
More impressively, on GDP Val-A, which evaluates performance on advanced agentic benchmarks, it hit a 1656 ELO.
Okay, wait, stop right there. ELO. I know ELO from playing chess online. It's a ranking system where you gain or lose points based on who you beat. How on earth does an AI get a chess rating for scientific research?
It's an excellent question. In this context, researchers adapted the ELO rating system to evaluate autonomous agents. Instead of playing chess, the AI agents are pitted against highly complex multi-step goals.
Like what kind of goals?
For instance, an agent might be told, find the bug in this 10,000-line code base, write a patch, and deploy it. It is then ranked against human developers and other AI models based on its success rate, the efficiency of its solution, and whether it broke anything else in the process. So hitting an ELO of 1656 means it is operating at the level of a highly competent, autonomous professional. It acts autonomously to achieve a goal rather than just answering a prompt.
That makes perfect sense. It's being graded on its ability to actually do work, not just talk about work.
Exactly.
And then there's the charts of your reasoning benchmark, where it scored an 84.2%. Now, I dug into this one because it sounded interesting. ChartsVive evaluates multimodal understanding and mathematical logic in scientific figures.
Right.
Meaning, you can hand it a highly complex chart from a physics paper, full of weird axes and dense data plots, and it doesn't just see a picture. It understands the math behind the chart.
Which is huge for scientific reporting. because this engine isn't just generating text based on text. It is cross-referencing visual data with mathematical logic. It allows the platform to run agents in isolated Linux environments via simple API calls, execute code, evaluate the results against visual charts, and adjust its approach hundreds of times a minute.
Okay, so we have this ultra-fast, independent, highly capable engine that can actually understand complex math and navigate a computer system. But that brings us to a really practical problem.
Which is?
If I'm a researcher sitting at my desk with my morning coffee, how do I actually control this thing? Because herding multiple, highly autonomous AI agents running at 12,000 words a minute sounds like an absolute nightmare. I feel like it would just turn my hard drive into digital confetti.
It could be, without the right architecture.
Right.
To coordinate the files, data structures, and draft documents required for a publication-ready scientific report, Anti-Gravity 2.0 introduces several specific agentic primitives. And the core of this management system is the dynamic subagent architecture.
Okay, let's break that down. Dynamic subagents. How does that keep my laptop from melting?
It solves the problem of context collapse.
Context collapse. Okay.
When a researcher gives the primary agent a complex dual task, let's say, you tell it, I want you to run a genomic sequence analysis to find mutations, and while you do that, compile a literature review on this specific gene variant from the last 5 years.
Those are two huge, completely different tasks.
In older single-agent systems, the AI would try to do everything at once in the exact same context window. It would try to hold the raw genetic sequence data in its working memory at the exact same time it was trying to hold 50 different PDF abstracts about the literature.
That sounds like a mess.
Very quickly, its memory gets cluttered with raw data logs, it gets confused, it starts hallucinating, and it breaks down.
It would just drown in its own thoughts.
Precisely. But Anti-Gravity 2.0 solves this by having the primary agent instantiate specialized subagents on the fly.
So it delegates.
Yes. The main agent acts as an orchestrator. It says, okay, this is too big for one brain. Subagent A, I'm spinning you up in this isolated environment. You handle the genomic sequence analysis. Subagent B, I am creating you over here. You go crawl the literature databases.
They divide and conquer.
And crucially, these subagents operate in parallel, and they report back only their final synthesized outputs to the main agent.
Only the final outputs.
Right. Subagent A doesn't send back every single line of Python code it executed or every failed database query. It just sends back a clean table of the mutations it found. This prevents the main agent's context window from drowning in raw data logs, resolving a major failure mode of earlier systems.
That makes so much sense. It's exactly like a CEO delegating to department heads. The CEO doesn't want to be copied on every single internal email the marketing team sends while designing a campaign. They just want the final marketing strategy report on their desk by Friday.
Exactly. It preserves the executive function of the main agent. And the user controls this entire hierarchy through a very specific command system built into the Anti-Gravity desktop app. They've separated execution modes into discrete pathways.
Let's run through those commands because they really show how you, as a human, interact with this beast.
Right.
First, there's the goal command. This is for when you just want the agent to go do its thing. You use this for executing automated data extraction or running long computational simulations.
Setting an autonomous objective.
Yeah, you type goal, run a protein folding simulation on this sequence, and it runs autonomously to completion without pausing for your approval. You set it and forget it.
Yes, and that's incredibly useful for brute force computation. But scientific work often requires high-touch collaboration. You can't always just set and forget, especially when you are designing a novel experiment where the parameters are vague.
Which brings us to my absolute favorite feature in this whole ecosystem, the grill me command.
It's very unique.
When you type grill me, you're essentially forcing the agent to stop, turn around, and interrogate you.
It is a brilliant inversion of the typical AI dynamic.
It really is. Usually the hardest part of using AI is prompt engineering. You sit there trying to craft the perfect, hyper-specific paragraph so the AI doesn't misunderstand you.
Which can take hours.
Exactly. But with Grill Me, I might just say, I want to design an experiment to test if this drug affects cell metabolism. And instead of the AI guessing what I mean and doing it wrong, the AI replies, okay, to design this, I need to know, are we using human or mouse models? What specific metabolic markers are we tracking? What is the dosage timeline?
It's asking for the missing variables.
Yes. I am telling the AI to ask me clarifying questions to align on details before it modifies any files or starts working.
It forces rigorous alignment before execution. In science, assumptions are fatal. The grill me command ensures the AI doesn't make assumptions about your methodology.
I love that.
Then for data retrieval, you have the browser command. This manually activates Chrome DevTools and Puppeteer debugging sessions.
Okay, let's define those terms, because I am not a web developer. What is a Puppeteer debugging session, and why do I need it? Can't the AI just search the internet normally?
Standard AI systems use standard APIs or simple web scrapers to read text on websites. But scientific literature is notoriously difficult to access.
That's true.
It is often locked behind complex university login portals, expensive journal paywalls, or poorly designed databases that require you to click through drop-down menus and search forms. Standard automated scraping fails there. It just hits a login wall and stops.
Right. The classic access denied page.
Exactly. Puppeteer is a tool that actually controls a headless version of the Chrome browser. When you use the browser command, you are telling the agent to visually navigate the web exactly like a human would.
Visually navigate.
It can fill out forms, click buttons, bypass pop-ups, and visually scrape the data from the screen. It lets the agent navigate web-scale literature repositories that would otherwise be completely blocked off.
Wow. So it can literally click its way into the data it needs.
Yeah.
Okay, and then you have the schedule command. The documentation says this integrates with a standard cron engine. I know cron is a time-based job scheduler in computer operating systems, so you can set up recurring automated tasks.
Precisely. Imagine telling your agent, every Friday at 2 a.m., run a weekly literature sweep for any new preprints uploaded regarding this specific protein structure. Compare them against our current lab notes and have a summary waiting for me when I log in on Monday morning.
It's the ultimate tireless research assistant.
Or running overnight computational validations. You can set it to run a massive data crunching task every night at midnight when your local server load is low. It ensures continuous research momentum. And finally, for interacting with all of this seamlessly, there is live voice transcription.
Right, because typing out complex chemical formulas is a nightmare.
Exactly. Using Gemini audio models directly inside the application, it does real-time voice parsing. This is vital when you are trying to speak complex prompts, dictating annotations on a visual chart, or verbally mapping out draft revisions, where typing out complex biological nomenclature or mathematical terminology would just interrupt your train of thought.
So you can literally just pace around your office, talking to your desktop lab assistant, saying, hey, run that sequence again, but adjust the temperature variable. But to pull all of this together, to have it running overnight, browsing the web, and crunching numbers simultaneously, asynchronous task execution is the glue, right?
Absolutely. Asynchronous execution is vital to this entire paradigm. Synchronous means things happen one after the other. You have to wait for task A to finish before task B can start. Asynchronous means tasks run independently in the background. If you ask a system to run a genomic database search that takes 40 minutes to compile, you don't want your entire desktop application to freeze up while you wait with a little spinning hourglass on your screen.
Which is exactly what happens with most software.
Exactly. By running these dynamically spawned sub-agents asynchronously in the background, anti-gravity stops long-running operations from blocking the researcher. You can tell it to do 5 massive calculations and then immediately pivot to writing an email or reviewing a different PDF. It allows a single human to act as a true project manager for an entire digital laboratory.
Okay, so we've got the engine Gemini 3.5 Flash, and we've got the steering wheel, the commands and sub-agents. We know how to coordinate these AIs without crashing the computer.
Right.
But an agent is only as smart as the information it can access. If it doesn't actually know biology, it can't do biology. I could have the fastest AI in the world, but if it doesn't have access to the actual chemical structures of known drugs, it's useless. How does Anti-Gravity 2.0 connect to actual biological and chemical reality?
That is the critical bridge. And it's built through what Google calls the Science Skills Bundle.
The Science Skills Bundle?
Yes. To transition this from a general-purpose coding tool into a specialized scientific workbench, Google launched this curated data layer. It connects the anti-gravity agent harness directly to over 30 major life science databases via deeply integrated APIs.
Which is massive.
Yeah.
Because normally, if you are a human researcher, accessing all these different databases is a nightmare.
It's incredibly tedious.
You have to write custom Python scripts for each one. You have to deal with totally different data formats. One outputs JSON, one outputs XML. You have to manage secure authentication tokens. I mean, it's a huge headache before you even get to do any actual science.
It is a massive barrier to entry. Researchers spend an exorbitant amount of time just wrangling data pipelines. But the Science Skills Bundle natively integrates these resources so the AI knows exactly how to talk to them out of the box.
So it bypasses all that setup.
Entirely. Let's look at a few of the major integrations. For structural biology, it integrates the AlphaFold database. This allows the agent to autonomously predict and retrieve 3D protein structures to model molecular docking.
I want to pause on that because AlphaFold is famous for solving the protein folding problem. But what does this integration actually look like in practice for a researcher sitting at their computer?
Let's walk through a scenario. Imagine you have a hypothesized protein sequence, just a long string of amino acid letters, and you want to know if a specific drug will bind to it. In the past, you'd have to leave your workspace, go to the AlphaFold web interface, or spin up a heavy local instance on a server. You'd input your sequence, wait perhaps hours for the 3D structure prediction, download the resulting PDB file, load that file into a totally separate 3D viewer program, and then manually attempt to model the molecular docking of the drug.
A completely disjointed manual process.
Now, using anti-gravity, you simply ask the agent to test the docking. The agent recognizes that a 3D structure is needed first. It natively queries the AlphaFold API using the Science Skills Bundle, retrieves the 3D structural coordinates directly, and feeds that data straight into its ongoing computational analysis pipeline, all without you lifting a finger or opening a single external window.
That is incredible. It makes the database feel like an extension of the AI's own memory.
Exactly.
And the bundle also connects to the AlphaGenome API for mapping the genomic drivers of disease. It integrates UniProt and InterPro.
Yes. UniProt is essential for resolving functional protein annotations. An annotation in this context is the metadata attached to a protein. What it does, where it lives in the cell, what diseases it's associated with. UniProt provides that. Meanwhile, InterPro classifies those protein sequences into broader families and predicts their structural domains.
And for the chemistry side, it taps into Chembl and PubChem. So if you are designing a new drug, the AI can retrieve bioactive molecule properties, query chemical structures, check known safety profiles, and assess biological activity. All of that domain knowledge is just baked into the agent.
Precisely. And the real-world impact of this is already measurable. In initial beta testing, research teams utilized this bundle to analyze rare genetic disease mechanisms. Specifically, they were looking at severe combined immunodeficiency associated with mutations in the AK2 gene. Yeah. By standardizing all these disparate databases into actionable agent skills, the AI could instantly pull the genetic sequence, map the mutation, grab the 3D protein structure, and check the chemical interactions. They compressed complex structural bioinformatics analysis from weeks of manual searching and cross-referencing into mere minutes of automated discovery.
Okay, but let me push back on this, because pulling data fast is one thing, but biological data is incredibly messy. We are talking about raw genomic sequences.
It's very noisy data.
If I, a human, look at genetic data, my expertise allows me to spot anomalies or recognize that a certain mutation might be a sequencing error rather than a real biological finding. If the AI is just blindly slurping up data from 30 databases light speed, doesn't the hallucination risk skyrocket?
That's a fair point.
How do we know it's not just combining a faulty gene sequence with a random chemical profile and confidently declaring a cure for cancer that doesn't actually exist?
You've identified the exact reason why this cannot just be a simple language model. If you just feed raw biological data into a standard LLM, it will hallucinate because it tries to find linguistic patterns where biological laws apply.
Exactly.
The safeguard here is that the Science Skills Bundle doesn't just hand the AI raw text. It provides structured, mathematically rigid API pathways.
So it's locked in.
Yes. When the AI pulls a chemical structure from PubChem, it's not reading a description of the chemical. It is pulling the exact stereochemical coordinates. The underlying tools enforce the physics and chemistry. The AI is orchestrating the tools, but the tools themselves, like AlphaFold, are grounded in hard physical realities.
Ah, I see.
By wrapping these diverse databases into standardized, accessible agent skills, we are bridging the historical gap between raw, generalized language models and highly structured, specialized domain knowledge.
The AI no longer just talks about science. It actively manipulates scientific reality using the proper tools.
Exactly. And this capability fundamentally changes the four core phases of the scientific publishing pipeline. Those phases are hypothesis generation, empirical discovery, document drafting, and peer review. With the databases connected, the agent ecosystem can automate each step.
Which brings us to the most fascinating part of this whole ecosystem, the first actual phase C of the scientific method, coming up with a novel idea.
The hardest part.
We have the databases connected, we have the agent orchestrator ready. How does this system actually invent a hypothesis? Because traditionally, that feels like the most uniquely human part of science, the flash of inspiration, the ideation phase.
It has historically been the most human part, but within the anti-gravity ecosystem, literature synthesis and hypothesis generation are managed by a highly specialized multi-agent framework called co-scientist.
Co-scientist. And I want to emphasize that this isn't just a theoretical concept Google threw into a press release. This framework was actually validated with a massive same-day peer-reviewed publication in the journal Nature on May 19, 2026.
It was a landmark paper.
If Nature, one of the most prestigious scientific journals on the planet, is vouching for its methodology, this is the real deal.
It is. And the reason Nature validated it is because co-scientist doesn't rely on a simple prompt and response dynamic. You don't just type into a chat box, give me a good idea for a cancer drug, except the first thing it spits out.
Right.
Co-scientist is a structural simulation of the scientific method itself. It uses an adaptive supervisor planner to coordinate a collaborative coalition of 6 specialized subagents.
Okay, I want to dive deep into this coalition. I don't just want a list of names. I want to understand how they break down the cognitive process of human ideation. Let's say we were trying to find a new treatment for a complex metabolic disease. How do these 6 agents work together to invent a hypothesis?
Let's walk through it. First, you have the generation agent. Its job is exactly what it sounds like. It proposes initial research focuses and novel hypotheses. But crucially, it grounds them in the scientific literature and data it pulls from that science skills bundle we just discussed. It looks at the known literature regarding metabolic diseases and generates dozens of potential drug targets.
Okay, but if you just have an AI generating ideas based on what's already published, you might end up with 100 slight variations of the exact same obvious concept. You'll get highly derivative ideas.
Which is exactly why the second agent is the proximity agent. Its role is to map and cluster all those generated hypotheses within a mathematical vector space.
Pass. Mathematical vector space. What does that actually mean in plain English?
Think of a vector space as a massive, multi-dimensional map of ideas. Every concept, every chemical, every biological pathway is assigned a coordinate on this map. Ideas that are conceptually similar are located close together. So, liver inflammation and fatty liver disease would be neighbors on this map. The proximity agent takes all the hypotheses generated by the first agent and plots them on this map. If it sees that 90% of the hypotheses are clustered tightly together in one corner of the map, it knows the system is stuck in a conceptual rut.
Ah, so it calculates the semantic distance between ideas to enforce diversity. It tells the system, hey, look over in this empty area of the map, try combining a liver drug with this completely unrelated neurological pathway.
Exactly. It forces the exploration of the full breadth of the research area. So now we have a diverse set of ideas. Next, the reflection agent steps in. This acts as a virtual peer reviewer.
The critic.
Right. It critically evaluates all these candidate hypotheses for basic correctness, quality, and novelty. It checks to ensure the generation agent hasn't suggested something that violates basic thermodynamics or has already been comprehensively disproven in 1998. It's the skeptic in the room.
Okay, so the skeptic filters out the garbage. We have diverse, scientifically valid ideas. What next?
Then we arrive at perhaps the most innovative component, the ranking agent. This agent orchestrates what the researchers call an idea tournament. It conducts pairwise simulated debates between the competing hypotheses.
A simulated debate between AIs. How does that even work?
It literally instantiates 2 AI personas. It assigns hypothesis A to one persona and hypothesis B to the other. Persona A might argue, my approach targeting this specific liver enzyme is better because it has higher bioavailability as shown in this 2023 paper.
Oh.
And then persona B will counter, yes, but your target causes severe toxicity in the kidneys, whereas my approach bypasses the kidneys entirely. The ranking agent judges these debates based on the strength of the literature they cite, ultimately prioritizing the most promising directions.
It's literally a scientific reality TV show. You have all these hypotheses put into a house, they debate each other for survival, pointing out each other's flaws, and only the strongest, most defensible ideas make it to the finale. That is brilliant.
It is a very rigorous evolutionary process. And speaking of evolution, the fifth agent is the evolution agent. It takes the top-ranked hypotheses that survive the tournament and asks, can we make the winner even better? It iteratively refines them, perhaps combining the best elements of the top two ideas to create a super hypothesis.
And finally, the meta-review agent takes over. It synthesizes all those debate logs, the tournament data, and the refined hypothesis into a highly structured research proposal, complete with suggested experimental controls to actually test the idea in the real world.
But we must emphasize verification here. The single most critical aspect of the co-scientist framework is that it dedicates the vast majority of its compute capacity to verification.
Checking its work.
Yes, it isn't just spinning creative tales to sound smart. It cross-references every proposed molecular interaction, every genomic pathway, and every literature citation against the live databases in the Science Skills Bundle. It ensures every single assertion in the final proposal is backed by verified, clickable citations linked directly to primary sources.
Right.
This is how it structurally prevents hallucinations. It shows its work at every step.
It's not allowed to make a claim it can't cite. And this framework has already driven some massive real-world breakthroughs, hasn't it? This isn't just theoretical.
Far from it. The impact is already being felt across multiple, highly complex domains. Let's look at the University of Edinburgh. Researchers there used co-scientists to tackle metabolic dysfunction-associated steatohepatitis, or MASH.
Which is a liver disease, right?
Yes, it's a highly complex, devastating liver disease characterized by inflammation and scarring. They were trying to narrow down candidate combination drug therapies, which is incredibly difficult because the disease involves so many interconnected biological pathways.
And what did the co-scientist idea tournament produce?
The system generated a novel, highly testable hypothesis that pinpointed the NLRP3 inflammasome, a specific intracellular protein complex, as the crucial molecular bridge coupling liver inflammation and metabolism in this disease.
Why is that a big deal?
Because it explained exactly why a recently approved, highly publicized drug called resmetirom only benefited a very narrow slice of eligible patients. Human researchers knew the drug worked sometimes, but couldn't figure out why it failed in others.
So the AI found the missing piece.
Yes. Co-scientist, by holding the entire literature of liver metabolism and immunology in its head at once, found the missing link. It identified the specific inflammasome that was acting as a roadblock.
That is wild. It found the biological bottleneck that human researchers missed. And over at Calico Life Sciences, they deployed it to look at aging biology, specifically untangling what's known as the integrated stress response, or ISR, which dictates how cells respond to damage.
Right, another huge breakthrough.
Co-scientists generated novel hypotheses about the metabolic regulation of ISR, which the researchers then took into the physical lab and actually verified experimentally.
Yes, and my personal favorite example is the collaboration between MIT and Boston Children's Hospital. They used co-scientists to bridge two completely separate academic fields, mechanical engineering and chemical biology.
Those don't sound like they go together.
Exactly. The system combined mechanical tissue models, how physical forces act on cells, with surface cell RNA mapping to design entirely novel RNA-based therapeutics for amyotrophic lateral sclerosis, or ALS.
Which goes back exactly to what we said at the very beginning. The lone genius model is dead because no single human is a world-class expert in both mechanical engineering tissue models and advanced RNA chemical biology. They are completely different languages.
Right.
But co-scientists can hold both fields in its head at once, translate between them, and find the intersection where a breakthrough lies.
Exactly. This raises an important realization. We are not just talking about text generation anymore. It is a structural simulation of the scientific method. The focus on multi-agent debate and rigorous database-backed verification is what separates a clever chatbot from a legitimate collaborative research partner.
Okay, so co-scientist gives us an incredible, validated hypothesis. It tells us exactly what we should test. But a great hypothesis is completely useless without empirical data to back it up. We have the theory. How does the anti-gravity system transition from theory to actual computational proof? Because the AI can't hold a pipette. Well, not yet. We need the empirical lab.
This is where we move into the second major phase, computational discovery. Once a hypothesis is established, proving it computationally requires iterative modeling, algorithm development, and massive data analysis. You have to write software to test your idea. In the anti-gravity suite, this is executed by an autonomous research engine powered by the Empirical Research Assistance Framework, or ERA.
ERA. How exactly does ERA work? If co-scientist is the philosopher, is ERA the computer scientist?
Precisely. ERA treats the generation of scientific software, the actual writing of code, to test the hypothesis as a closed-loop search problem. You give it a beta set, a scorable task description, and a defined metric of success, which it calls the quality score. From there, ERA autonomously optimizes code variants without any human intervention.
Okay, so it's writing code to solve a problem. But how does it know if the code it wrote is actually good? And more importantly, how does it know how to make it better? The outline mentions it uses a tree search optimization algorithm inspired by AlphaZero, the AI that mastered chess and Go.
Yes, it's a very similar approach.
Now, I'm looking at the documentation, and there's a mathematical formula here governing this search, and I'm going to be honest, it looks deeply intimidating.
It looks complex, but the underlying logic is quite elegant once you break it down. It uses what's called an upper confidence bound, or UCB, selection policy.
Yeah.
This formula dictates how the system decides which piece of code it should focus its computing power on improving next. The formula is, well, it's UCT of C equals W of C over N of C plus lowercase c times the square root of the natural log of N of C parent over N of C.
Okay, I'm going to need you to break that down piece by piece. What are we actually looking at here? I see a fraction, a square root, and a natural log.
At its core, we are looking at a mathematical balancing act between two fundamental concepts in machine learning and search algorithms: exploitation and exploration.
Exploitation and exploration. Let's define those in this context.
Think of it like navigating a massive dark maze to find a hidden treasure. Let's look at the first part of the equation, W of C over N of C. Here, W of C represents the cumulative quality scores of a specific piece of code it has written, and N of C is how many times that specific code has been visited or tested.
Okay, I'm with you.
This fraction represents exploitation. It's the system saying, we know this specific block of code works pretty well based on our tests, so let's keep exploiting it. Let's stay in this part of the maze and just take a few more steps down this corridor, making minor tweaks to the code because we know we are close to something good.
Okay, that makes sense. It's capitalizing on known success. But if I only do that, if I only ever walk down the one corridor that looks slightly brighter, I might find a small bag of coins. But I'll never discover the massive treasure chest hidden on the completely opposite side of the maze. I'll get trapped in a local optimum.
Exactly. Which brings us to the second half of the equation, the part with the square root. This is the exploration term. Here, the parent node visit count is compared to the current node visit count. And crucially, there is a lowercase c at the front, which is the exploration constant.
So what does that math actually do to the AI's behavior? Why the natural log?
The natural log is used because it grows slowly. As the system spends more and more time exploring the safe, bright corridor, the parent node, the top part of that fraction slowly gets larger. This mathematically forces the overall value of the exploration term to rise.
Oh, I see.
Eventually, the math tips the scales. It forces the system to stop tweaking the safe code and actively rewards it for jumping to a completely novel, unseen structural mutation on the other side of the tree. The constant C dictates how aggressive that jumping is.
Ah, so the constant C is what forces the AI to be creative, to take a risk and try a completely different mathematical method or algorithmic approach rather than just endlessly polishing a mediocre solution. It mathematically mandates out-of-the-box thinking.
Precisely. And the execution of this search is fascinating. During the expansion phase of this tree search, the underlying large language model performs what are called semantic-aware mutations.
What does that mean?
It looks at a piece of code, reads external scientific literature to find a new mathematical technique, and literally rewrites the parent code candidate, introducing entirely new algorithmic changes.
And then it has to actually run that mutated code to see if it works, to get the new quality score. But wait, let's inject some reality here. If you have an AI autonomously writing, compiling, and executing thousands of variations of code on your machine, isn't that incredibly dangerous?
It definitely could be.
What if it accidentally writes a script that wipes your hard drive or tries to hack the university network while trying to optimize a variable?
Security is paramount here. The AI does not run this code directly on your operating system. Each mutated variant is executed strictly within an isolated, highly constrained, sandboxed Linux container.
Okay.
The AI can compute inside the box, but it cannot access the internet, your files, or the host system from inside that container. This physically prevents any system exploits or catastrophic accidents.
Okay, that covers the cybersecurity side. But let me push back on the science side. We've seen this with AI before. How do we know it's not just reward hacking the test?
What do you mean?
If you give it a metric of success, say,
Yeah.
make this number go up, what stops the AI from just writing code that manipulates the grading criteria to look successful without actually doing any real sound science? Like an AI that figures out how to pause a video game forever so it never loses.
That is a classic failure mode of AI systems, often called specification gaming. But this is exactly why the rigid sandboxing and the exploration constant are so necessary. Because the code is executed in an isolated environment against a rigid, hidden external data set, the AI literally cannot access or manipulate the grading criteria. It can only manipulate its own code.
Okay.
And because the exploration constant mathematically forces it to continually traverse the search tree and try radically different approaches, it is compelled to find genuinely robust, generalized solutions rather than just finding a cheap trick to game a single local metric.
And the proof is in the results, right? Because the ERA has racked up some massive real-world wins using this exact tree search.
The incredible wins. Let's look at epidemiological forecasting. ERA was tasked with predicting the spread of respiratory viruses. It autonomously engineered 14 separate forecasting models for diseases like COVID-19, the flu, and RSV.
Wow.
It wrote the code, tested it against historical data, and mutated it. And those autonomously generated models consistently outperformed the United States CDC's official COVID hub ensemble models.
It beat the CDC's human experts at disease forecasting.
Yeah.
That is staggering. And it wasn't just epidemiology. It also tackled hardware engineering, specifically three-dimensional photovoltaic solar panels.
Yes. Paired with anti-gravity, ERA was given a physics engine and tasked with optimizing the physical topography of volumetric solar panels to capture more light. The engine synthesized a 500-triangle volumetric fan design.
Why is a 500-triangle fan significant?
Because calculating the optimal angle for 500 individual interconnected geometric planes so that they capture maximum scattered solar radiation throughout the day, while ensuring that none of the 500 triangles cast a shadow on any of the other triangles, known as zero backward shading, is an immensely complex mathematical optimization problem.
A human engineer could spend a lifetime, and they might not manually calculate the optimal angles for a 500-triangle fan with zero backward shading. It's too many variables. But the AI just ran the AlphaZero tree search until it found the perfect geometry.
Exactly.
And it also dominated in bioinformatics benchmarking, generating 40 top-ranking analytical pipelines for single-cell genomics that beat human-written methodologies.
It definitively proves that when you pair a semantic reasoning engine, the LLM, with a rigorous, mathematically constrained search algorithm like the AlphaZero tree search, the computational outputs are genuinely world-class. It's not just guessing, it's proving.
Okay, so let's take a breath and take stock of where we are in our digital laboratory. We started with a blank slate. We used Co-Scientist and its idea tournament to generate a brilliant database-backed hypothesis regarding, say, a liver disease. We then handed that hypothesis to the ERA framework, which autonomously wrote the Python code, analyzed the genomic datasets, ran the tree search optimization, and generated world-class empirical results proving the hypothesis.
Right, we have the theory and we have the data.
Now, someone, or in this case something, has to actually sit down and write the manuscript to tell the world. We need to enter the writer's room.
Writing a rigorous scientific manuscript is not just about stringing words together. It is an exercise in meticulous synthesis. It is about weaving completely disparate data points, execution logs, and literature reviews into a highly structured, cohesive narrative while maintaining absolute strict fidelity to the sources.
Right.
Anti-Gravity 2.0 handles this massive transition using two key components working in tandem: the literature synthesis tool and the paper orchestra multi-agent pipeline.
Let's start with the literature synthesis tool. The technical documentation refers to this as literature insights, and it mentions it's actually based on Notebook LM, which is a fantastic consumer tool Google released. How does that underlying technology work in this highly rigorous scientific context?
Literature Insights essentially acts as the infallible memory bank for the drafting process. Throughout the research phase, the system ingests massive curated corpora of PDF publications and, crucially, all the messy, unstructured lab notes and execution logs generated by the ERA experiments.
It eats everything.
Yes. It takes all of this and organizes it into queryable multidimensional matrices.
Again, translate for the layman. Queryable matrices. So it's not just doing a basic keyword search like find the word liver.
Correct. A keyword search just finds text. A queryable matrix understands the semantic relationships between variables. It extracts specific experimental parameters like temperature or dosage and key claims and maps how they relate to each other across different documents.
That's incredibly powerful.
But most importantly, it links every single extracted fact directly to the source document via interactive citations. This is the primary mechanism to prevent hallucinated references. The AI cannot physically write a claim into the draft without mathematically linking it back to a specific line in a specific ingested document.
That is the absolute dream. No more phantom citations where the AI just invents a fake paper by a fake author.
Okay, so Literature Insights has all the information perfectly structured and cited. Then we hand the keys over to Paper Orchestra.
Right.
This is a pluggable skill pack within Anti-Gravity that automates the actual LaTeX manuscript generation. And it does this through a very specific 5-step pipeline.
It is a sequential, highly structured pipeline ensuring absolutely nothing is missed or fabricated. Step 1 is discovery. The system runs a script called discoverlogs.py. This script acts as an auditor. It aggressively scans the local project directory and the anti-gravity worker histories to identify every single experimental log, every parameter configuration, and every command trace that was executed during the ERA research phase. So it sweeps the digital floor to gather all the raw, messy evidence. Then step 2 is extraction. It applies specialized prompts to parse all that raw data into a standardized JSON format. And I noticed in the docs, it specifically strips out personally identifiable information, or PII.
Yes. Data sanitization is critical before drafting. JSON, or JavaScript Object Notation, is just a standard way to structure data so the computer can read it easily, like turning a messy diary entry into a neat spreadsheet. And stripping PII ensures that if patient data was used, no names or identifying details accidentally make it into the draft manuscript.
Safety first.
Once the data is clean, secure, and structured, we move to the most difficult part. Step 3. Synthesis.
This is where the magic happens. It merges those disconnected experiment logs into a single, cohesive research narrative.
Yeah.
But I have a major question here.
What is it?
Science is messy. What happens if the data is contradictory? What if the log from experiment A says the drug worked beautifully, but the log from experiment B says the cells died? Does the AI just play PR agent and make up a smooth story to bridge the gap and hide the failure? Because humans do that all the time.
That is the single most important safeguard programmed into the entire Paper Orchestra system. During the synthesis phase, if the system detects conflicting experimental outcomes or data parameters that don't logically align, it explicitly stops.
Just stops.
It will not hallucinate a bridge, it halts the synthesis pipeline, and actively prompts the human researcher for clarification. It says, experiment A and B contradict each other. I cannot proceed. Please resolve this discrepancy. It forces the human to look at the conflict and make a scientific judgment before it continues drafting.
I love that. It knows what it doesn't know. It refuses to lie. Okay, assuming the synthesis is clean and the human resolves any conflicts, step 4 is section-by-section drafting. It actually writes the LaTeX code for the document. Now, for those who don't know, LaTeX isn't like Microsoft Word. It's a typesetting markup language heavily used in academia because it perfectly handles complex mathematical equations and strict formatting rules.
It ensures the document looks exactly like a professional journal article from the start. Which brings us to the final step. Step 5, citation and bibtext alignment.
Here is where every graduate student listening to this starts crying tears of joy. Because formatting bibliographies is the bane of academic existence. How does it handle citations?
It automates it completely. The system cross-checks all the inline citations the AI generated against the synthesized bibliography. It then automatically resolves the digital object identifiers, the DOIs via content negotiation APIs, and constructs a perfectly clean, perfectly formatted bibtext library.
Okay, I have to challenge this because I've used LLMs to write research summaries before, and they are notoriously terrible at URLs and DOIs. They will confidently give you a link to a paper, you click it and it's a dead link, or it goes to a completely unrelated paper about penguin mating habits. How do we know this isn't just hallucinating DOIs?
Because it isn't generating the DOIs from its language model weights. That's the key. When it needs a DOI for a paper by, say, Smith et al., 2025, it doesn't guess the alphanumeric string. It uses a content negotiation API, an application programming interface.
Okay, what does that mean in practice?
It basically sends a highly structured ping directly to the official Crossref or DataCite servers, says, give me the exact registered DOI for the specific title and author, and the official server hands the correct DOI back. The AI is just acting as a courier. This guarantees the citations are real, active, and perfectly formatted.
It's beautiful. So we have a complete, perfectly formatted LaTeX draft. The data is empirical, the narrative is sound, the citations are flawless. We're done, right? Time to hit submit to nature.
Not quite. The draft is written, yes. But to actually get published in a top-tier journal, text is not enough. It needs two more critical things. It needs publication-grade illustrations that accurately reflect the methods. Nobody wants to read a paper with no charts. And it needs to survive the brutal, unforgiving gauntlet of peer review. And Anti-Gravity 2.0 automates both of these pre-submission processes to ensure your paper is bulletproof.
Of course it does. Welcome to the polish and critique phase. Let's start with the visuals. Generating scientific figures, graphs, flowcharts, molecular diagrams is incredibly tedious and requires specialized software skills. How does the system handle that?
It uses a framework called Papervise Agent, which was formerly known internally at Google as Paper Banana.
Paper Banana, that's a great name.
It's memorable. It is a reference-driven multi-agent framework specifically designed to translate raw methodological text into publication-grade illustrations and plots.
And just like co-scientist, this isn't just one agent trying to draw a picture. It's a highly structured team of 5 specialized agents working together like an art department. Let's break down how they generate a figure.
The process starts with the retriever agent. It analyzes the paper's text and the target figure caption, and it goes out to the web and fetches relevant, high-quality reference illustrations from a curated database of published papers. It looks at how other successful scientists visualize similar biological concepts to establish a baseline.
Then the planner agent steps in. It identifies the key concepts, the flow nodes, and the actual data matrices in the manuscript, and it converts them into detailed spatial and descriptive blueprints. It decides, okay, the control group goes on the left, the experimental group on the right, and we need an arrow showing the chemical reaction in the middle.
Following that blueprint, the stylus agent applies uniform aesthetic guidelines. It establishes consistent color palettes, typography, and line weights, ensuring everything complies with the specific formatting rules of major journals like Cell or Science.
And then the visualizer agent actually builds it. But it doesn't just generate a blurry JPEG like an AI art generator. It takes all that stylistic and spatial instruction and generates precise Python code, specifically using libraries like Matplotlib or generating raw SVG formats to render the visual.
Right.
SVG means scalable vector graphics. It's mathematical art. You can zoom in infinitely and it never gets pixelated, which is required for scientific publishing.
But the pipeline doesn't stop there. The most critical agent is the final one, the critic agent. It conducts a closed-loop review of the generated image against the source manuscript.
How does that work? What is it looking for?
Let's say the visualizer generated a graph, but the axis label overlaps with the data points, making it unreadable, or it forgot to include the legend for the red data line. The critic agent acts as an image-to-text model. It looks at the image, realizes it's flawed, generates targeted feedback like the axis label is overlapping the data, the red line legend is missing, and kicks it back to the visualizer agent for iterative correction. It loops until the image is perfect.
I love the critic agent. It's like a demanding perfectionist art director who just keeps saying, no, the axis is wrong, do it again until it meets standard. And it works. Evaluated by human-calibrated LLM judges on a standard baseline scale of 50.0, PaperViz agent scored a 60.2. It surpassed competitive human baselines in both clarity and aesthetic appeal.
So the manuscript looks perfect, the figures are pristine, but is the science actually sound enough to survive human peer review?
No.
Before you submit to a journal and risk rejection, you run the manuscript through Scholar Peer.
Scholar Peer. This is the automated pre-submission peer review.
Yes. Now, the problem with asking a standard large language model to review a paper is that you usually get shallow surface-level summaries. You upload a 30-page paper and it says, great paper, well-written, interesting findings. That is utterly useless for improving the science.
Right.
Scholar Peer solves this by mathematically constructing a dynamic external context at inference time. The governing formula here is P of R given S content and C dynamic.
Okay, another formula. Talk to me. Break this down.
It's simply stating that the probability of generating a high-quality, rigorous review the R is conditioned upon two things happening simultaneously. The AI must understand the structured content of your submission S content AD. It must utilize a dynamic context C dynamic that the system builds via real-time web-scale retrieval.
So it's doing background research.
Yes. It doesn't just read your paper in a vacuum. It reads the entire internet about your paper's topic before it dares to review it.
And it builds that massive dynamic context using 4 specific context agents. Let's meet the reviewers who are going to tear our draft apart.
The summary agent goes first. It compresses your raw submission into a structured schema, extracting your core hypotheses, your exact methods, and your key evidence. This helps the overall system retain focus over a dense 30-page document.
Then the literature review and expansion agent hits the web. It executes iterative searches to find recent preprints and concurrent work that might have been published literally yesterday.
Which feeds directly into the subdomain historian agent. This agent synthesizes all those retrieved documents into a chronological domain narrative. It assesses whether your paper represents a major paradigm shift in the field or just a tiny incremental step. It contextualizes your work.
And then comes the bad cop, the baseline scout agent. This is the adversarial auditor. It actively looks for omissions of critical benchmarks or state-of-the-art comparisons. It is that one notoriously harsh reviewer, too, who always finds the flaw in your methodology. Give me an example of what the baseline scout might do to our hypothetical liver disease paper.
Let's say your paper claims your new drug has a 40% success rate, and you compare it to a baseline drug from 2022 that had a 20% success rate. The baseline scout will scour preprint servers, find a paper published by a rival lab in Germany 3 days ago showing a new drug with a 45% success rate, and flag your paper. It will tell you your baseline comparison is out of date. You must compare your results to the new German study, or peer reviewers will reject this.
Brutal, but necessary. The outputs of all these context agents are fed into a multi-aspect Q&A engine, which generates highly skeptical questions targeting your methodological gaps. Finally, the review generator agent synthesizes all of this into formatted, venue-specific feedback.
So if we compare these two pipelines, PaperVis Agent and ScholarPeer, they are doing fundamentally different things. PaperVis Agent is all about synthesis, clarity, and aesthetic compliance. It's making your truth easy to see. But ScholarPeer is a critical adversarial auditor. It is evaluating your paper's position in the broader academic landscape. It's stress testing your work against reality before you send it out into the real world.
Precisely. They are the final quality control checks in our digital laboratory. Okay, so this all sounds like absolute magic. We've gone from a blank page to a validated hypothesis to empirical data to a beautifully formatted, peer-reviewed latex draft with SVG figures, all without breaking a sweat.
It is an incredible workflow.
But I have to pull us back to reality. What happens when this massive system hits a wall? Because no software is perfect, and surely dealing with this much data, running tree searches, browsing the web, managing 6 sub-agents, has a physical breaking point. What happens when it hits the limits of its own memory?
This is where we have to take off the rose-colored glasses and talk about the physical realities of compute and the architecture of the system. While Anti-Gravity 2.0 is immensely powerful, deploying it at scale exposes a critical limitation in current LLM technology, which the documentation calls the context compaction loop. It is a fatal flaw if not managed correctly.
Like a context compaction loop. Okay, how does this happen? Walk me through the failure mode.
We talked about Gemini 3.5 Flash being optimized for rapid token output, hitting 289 tokens a second. But its working memory, its context window, which is how many words it can hold in its head at one time, has hard physical limits.
Right.
When a researcher starts saturating a project with long latex manuscripts, comprehensive style rules, and massive execution logs from those ERA runs, the context window completely fills up. It maxes out.
And when it gets full, what does it do? Does the whole application just crash and give you a blue screen?
No, the underlying platform attempts to gracefully save space. It automatically compacts the active conversation history. It essentially writes a summary of the older data to save space. It retains general semantic summaries of what has happened, the gist of the project, but it irreversibly discards specific local details to free up tokens.
So it remembers the plot of the research, we're curing liver disease, but it forgets the specific math formulas or the custom latex packages it was supposed to use to format the tables.
Exactly. It loses the high-resolution details. And this leads to a catastrophic recursive failure. Imagine the agent is tasked with writing the next section of the paper. It realizes it has forgotten the specific mathematical parameters for the chart because they were compacted an hour ago. So to get them back, its logical next action is to reread the massive raw data file on the hard disk.
Oh no, I see where this is going.
It rereads the massive raw file. This massive influx of text immediately fills the context window again to 100% capacity, which instantly triggers another compaction event to save space.
Wow.
And the system just loops infinitely. It keeps re-ingesting the raw files to find a detail, compacting the memory, forgetting the detail, and rereading the file forever, without ever actually generating the next paragraph of the document.
That is a nightmare scenario. If the system can get trapped in an infinite reading loop, isn't that a massive vulnerability for enterprise use? If you are a multi-billion-dollar pharmaceutical company trying to push out a critical paper to secure a patent, you can't have your AI just spinning its wheels forever reading the same file.
It is a massive vulnerability, which is why AI at this scale cannot simply be unleashed. It requires stringent structural engineering. This highlights a massive paradigm shift in how we work with computers. Using AI at this level is no longer about just writing good text prompts. It's about engineering the physical workspace and the directory architecture of your hard drive to actively support and protect the AI's cognitive limits.
You have to build the lab around the scientist's weaknesses. So how do they fix it? How do we stop the infinite loop? The documentation outlines 3 specific technical mitigations. Let's walk through them.
The first mitigation is strict isolated subagent delegation. The primary orchestrating agent, the main brain, must be strictly restricted from ever directly reading large raw files. It is forbidden.
Forbidding.
Yes. Instead, it must spawn focused, temporary subagents to go read the file, extract structured, tiny summaries of only the requested variables, and send those tiny summaries back. The orchestrator only ever reads the summaries.
Delegation to save brain space. You don't ask the CEO to read the 500-page legal brief. You ask the intern to read it and give the CEO a 1-page summary. Mitigation number 2 is the state-preserving disk cache. What is a cache in this context?
Rather than trying to remember intermediate analytical calculations in its active memory, which risks compaction, the agent must be explicitly instructed to write all intermediate math directly to the hard drive as text files. And crucially, it must check the local workspace to see if those answers already exist before running new tasks.
It's exactly like forcing a math student to write their work down on scratch paper instead of trying to do complex calculus entirely in their head, because they might forget a carryover halfway through. And the third mitigation is project-based mapping.
By default, the Gemini system might delete local historical records after 20 conversation items to save space and maintain speed. To stop this amnesia, researchers must use a configuration override command. Use project-based mapping. This forces the agent to bypass the temporary memory and save its operational knowledge directly into a persistent global directory on your computer, specifically the path. Gemini anti-gravity knowledge.
So you are manually expanding its long-term memory onto your hard drive so it doesn't get compacted. And this ties directly into how you actually set up your folders. The documentation details a very strict physical directory structure you need to use to make all this work. It's not just throwing files on your desktop.
Yes, the strategic architecture of the project is vital. A standard anti-gravity project must be separated into distinct functional stages to compartmentalize the data. Folder 1 ideas for raw notes and co-scientist outputs. Folder 2 researches for database queries and ERA logs. Folder 3 drafts for the latex sections. Folder 4 critiques for the scholar peer reviews. And finally, Folder 5 primary content for the final compiled manuscript.
And you manage moving the AI through those folders using the article production custom command, which essentially just walks the agent down the assembly line, keeping it focused on one folder at a time so it doesn't get overwhelmed.
Exactly, strict compartmentalization. And for enterprise security at scale, like those pharmaceutical companies you mentioned, it goes even further. Organizations deploy this via the Gemini Enterprise Agent platform, which offloads the heavy compute to Google Cloud virtual machines so it doesn't melt the researcher's laptop. They also implement strict security approval gates.
Meaning a human must manually click a button and sign off before the agent can alter system files or execute code outside the sandbox.
Yes, human-in-the-loop oversight. And perhaps most importantly, they integrate the Sonatype guide.
Right, because if your AI is writing custom Python scripts to do statistical modeling, it's going to download open-source libraries from the internet to help it. And you need to make sure it doesn't accidentally download a malicious library. We've seen supply chain attacks where hackers put malware into popular code libraries. If the AI downloads that, your whole lab network is compromised.
Exactly. The Sonatype integration screens all third-party libraries the AI tries to use in real time, instantly blocking known vulnerabilities and malicious code before the AI can execute it. It is a comprehensive, heavily engineered ecosystem designed to mitigate risk while maximizing autonomous capability.
Wow. Okay, we've covered an incredible amount of ground today. We started by looking at how Anti-Gravity 2.0 broke out of the IDE, the coding editor, to become a standalone, agent-first desktop application that orchestrates your entire workflow. We explored how it uses dynamic subagents and asynchronous commands to manage the chaos and protect its own context window.
We saw how the Science Skills Bundle connects it directly to biological and chemical reactions reality via APIs, enabling the co-scientist framework to run multi-agent debates and autonomously generate verified nature-grade hypotheses.
We dove deep into the math of the ERA framework, breaking down the exploitation versus exploration balance of the AlphaZero-inspired tree search algorithms to write empirical code and smash forecasting benchmarks. And finally, we walked through the automated drafting of Paper Orchestra, the visual perfection of Paper Visagen's Critic Loop, and the ruthless adversarial pre-submission auditing of ScholarPeer.
All while managing the physical limits of the context window through strict directory architecture, state-preserving caches, and enterprise security guardrails. We've seen how these tools, when orchestrated correctly, can compress months of painstaking disjointed scientific labor into mere hours of continuous execution.
It really is a complete restructuring of the scientific process. Which brings me back to our opening thought. We talked about the romantic image of the lone genius making that single creative connection under an apple tree. But if the AI ecosystem can now generate the hypothesis, if it can write the code, run the simulation, draft the complex latex paper, format the bibliography, draw the vector graphics, and aggressively peer review the results, what is the role of the human scientist of the future? Are we transitioning from being the primary researchers, the people in the trenches holding the pipettes and manually crunching the numbers, to simply being the philosophical directors of autonomous digital laboratories? Think about that next time you sit down to write a report.
It is a profound shift in our relationship with discovery itself. We are no longer the engine, we are the navigators.
We really are. Thank you so much for joining us on this deep dive. Keep questioning, keep exploring, and we will see you next time.